And let's see what that normal distribution looks like. So I'll put this up here. All right. So we want to substitute in 550 right in here and 100 right in here. All right. So let's put in e to the negative. Let's put it all in parentheses. X minus mu is 550, and all of that squared. And that divided by 2 times sigma squared. And so I'm just going to make that 100 squared, so 10,000. And I'm just going to make sure that's all in parentheses here. Whew, a lot of parentheses. All divided by square root of 2 times pi times sigma squared. So I'm just going to put in my 10,000 again. All right. So what we should see from this is the mean being at 550 and the standard deviation being at 100. All right. So let's see. And the nice thing about Wolfram Alpha is that just in case I missed a parenthesis somewhere or something, it'll rewrite the input for you in a more standard form instead of this like sort of crazy like linear way, so that you could check and see, oh, did I miss a parenthesis or something? All right, so let's see. Is this, so that should be about where 550 is, and yeah, that looks like the middle, the center of that curve. And not only that, but from 550, if you go out to 450 or 650, that does look like about 68% of that curve. So what we see here is that this function, if you substitute in any mean and any standard deviation, it will effectively draw or represent this normal distribution for you. All right, so that's the PDF. But what this gives you is at every point, what is the probability for that particular value of x? But let's move on to cumulative distribution function. When we want the cumulative distribution function, we don't just want that curve. Instead, what we want is sort of a cumulative adding up of all the areas that came before. So what we're really looking for is that curve, right? And at any point, I could tell you the percentile that we're at. So here it sort of encapsulates all the space that came before it. All right, so as we talked about before, because we want that cumulative area, all we have to do now is take the integral of phi. And so what we represent we represent the cumulative density function as big phi now, so uppercase phi rather than lowercase phi. And we put in x, of course. And all we do is we take the integral, and we take the integral from negative infinity up to, x, whatever x is, and that will give you the area so far of phi. And obviously you could actually get the integral, but I'm just going to leave it at this because I just really want you to know what the function actually is meaning, right? The meaning is just the integral of phi, which we talked about, of little phi that we just talked about. And what that gives you is sort of this idea of the area so far, area up to this point of x, whatever x is. And because we're talking about for a standard normal distribution, that's why I'm using that phi. Else, I would use the f of x for the normal distribution function. All right, so that's CDF. That was a little bit easier. All right, now let's go on to some examples. So here's example number 1, and it's just talking about frequency graphs. It's not actually talking about the CDF or the function. So here it says, estimate the score that falls at the 40th percentile. And percentile is a word that we save just for cumulative frequencies or cumulative relative frequencies. So here, one thing that makes this chart really easy to use is that we could just go up to 40th. I'll use a different color. And we could go all the way across and then go down. And we sort of get a rough approximation of that score. And so that score is about, a little bit less than 500, so 480, let's say. So that's the score that sort of falls at the 40th percentile. If you wanted it a little bit more than 40, you could just round up to 500. If you want a little bit less than 40th percentile, you could round down to about 450. All right, here's example 2. In problems with the normal distribution, the mean, the standard deviation, x, and the probability of x, these things are involved, right? And like a puzzle, if you have 3, you could figure out the 4th, right? So here we have a couple of things that are missing, right? But it gives you some of the other pieces, and so we have to figure out the pieces that are missing. So I'm just going to take a look at my first line. It just says the mean is 3, the standard deviation is 1. I have an x value. What is the probability at that x? I'm just going to pull up a regular old Excel sheet. And I've just labeled it with mean, standard deviation x, and probability of that x. And I'm also going to just write in z, because often we need to find z in order to use the tables in the back of the book. And so I'm going to write in z. So the mean here is 3, the standard deviation is 1, x is equal to 2, right? So if we thought about that in a normal distribution picture, the mean would be 3, standard deviation is 1. So this would be 2, 4, right? And since x is at 2, it's asking for this, right? And so it should be about, I would guess, 16%, just using the empirical rule. But let's find out exactly how much that is. All right, so if you wanted to use the special Excel functions, you could actually just use norm dist, because you have everything you need. You have your x, you have your mean, you have your standard deviation, and if you want the cumulative probability, you just write true, which is what we want. Yeah, and we get about 16%, 0.159-ish, right? Another way you could do it is by finding the z-score and then looking it up in the back of your book. You could use standardize, or you could actually find the distance between the x and the mean and divide that by the standard deviation to get how many standard deviations away, right? So it's 1 standard deviation away on the negative side. And if I didn't want to use this function, I could just use norms dist, and all I have to put in is my z-score. And I get the same thing, right? So those are 2 different ways you could do it. You could also look up that z-score in the back of your book. All right, let's do the second line. Here we have the mean, but now we don't have the standard deviation. We do have x, which is 0.1, and when x is less than 0.1, it's at 0.18. 0.18. Okay, so let's draw this, let's sketch this out to sort of help ourselves. I'll draw it in a different color. So that's this one. So here the mean is 10, but I don't know what to write here, right? But what I do know is that around 18%, which is a little more than 16%, right? Around 18%, that x is 0.1, right? So, so my question is, what is my standard deviation, right? What is this jump such that at 18%, that's 0.1? Well, we have all the pieces that we need. One thing that might be helpful to do is find the z-score, because the z-score formula has the standard deviation. And we have all the other pieces, like the mean and the x. And so once we know the z-score, then we could really easily find out the standard deviation. So I'm just going to use my norms inverse, right? Which will give, if I put in the probability, it'll give me the z-score. Or you could also look up in the table in the back of your book, look for 18% and find the z-score there. So here I find that my z-score is negative 0.91. So it's a little bit closer to the mean than negative 1, right? But it's almost negative 1. And once I have that, then I could easily find my standard deviation function just by using my z-score formula. Because the z-score formula is just x minus mu all over the standard deviation. Or let me use the correct notation here. All over sigma. Right? And what I want to do is solve for sigma. And so here I could just multiply by sigma on both sides, divide by z on both sides, and I could get sigma equals x over mu, x minus mu, all over the z-score, right? And that I can easily do either in Excel or on your calculator or in your head. All right, so I just take x minus the mean, all divided by the z-score. And I get 10.81. And that makes sense because if I went out about 10.81, I would be at negative 0.81 right here at the first standard deviation out. And this is just a skosh more than that. So, so that answer makes sense. All right. Now let's go to the third problem. My standard, now I'm missing my mean, but I have my standard deviation. I have my x, which is negative 0.6. And I know that the probability where x is less than negative 0.6 is 35%. And so I'll put in that. And let's just sketch that out just so we sort of can check whether our answer that we get is reasonable. So now we have no idea what this middle value is, but we do know that each jump is about 3 away. And although we can't tell, where to write that 0.6, we could tell by this percentage, okay, it can't be out here, it must be somewhere in here, such that this is about, maybe a little more even, that this is about 35%, right, of that curve. It's not quite half of that half, it's a little bit more than half of this half. Okay, so the question is, what is this mean, right? And we know at that point it's negative 0.6. So whatever my mean is, it's got to be bigger than negative 0.6, just because we know that this isn't quite half yet, and if we had the middle, that's the mean. So once again, it's helpful to find the z-score because the z-score formula has the mean in it, and so it's easy to find the mean once we have the z-score. And so once again, I'm just going to use norms inv and put in my probability. And I get this z-score of negative 0.38. And that makes sense. That's in between 0 and negative 1. And so now let's use that in order to find our mean. If you want, you could just derive it from this again. So instead of going from z x, so now we want to isolate mu. It would be z sigma equals x minus mu. I'm going to move the mu over to this side and move this over to this side. Z. And so that's what I need to do in order to get my mean, mu. And so I'll take my x and subtract the z-score times the standard deviation, and I get a mean of 0.56, right? And that makes sense. That's bigger than 0.6, and since there's a distance of 3, that would make sense for 0.6 to lie in between 0.55 and negative 2, let's see, negative 3.55, 2.55, something like that. Anyway, so this roughly makes sense to us. So once you write in these answers, you're good to go. All right.